Okay, today we're going to be talking about solving exponential and log equations with the context of word problems and real world type of stuff. So let's jump into it. Now, first of all, the only thing that's going to be a little bit different here with some of these formulas that we've used here in the past is this growth and decay using E. And with this equation here, this is basically if something is continuously growing, or I guess decaying. So that'll be kind of helpful here in a minute. So let's look here at this first situation and then talk about how we can use logs to help ourselves solve it here. So you got 150 is deposited into a savings account with an interest rate of 5.5% compounded continuously. How long will it take for the amount to double? Okay, so we're going to, first of all, choose the correct formula here. So since it is compounded continuously, we're going to use the compound continuously formula right there. So this will be A equals P and then E raised to RT. Okay, and then we're going to plug in everything we know. So we know that the starting amount is $150. Okay, and then it's asking how long will it take for it to double. So actually, we're going to say it's equal to 300. And then we know our rate is 5.5%, which remember, we got to change that to a decimal. So that would be 0.05 right there, 0.055 actually. So that'll be your rate right there, and then raised to t. Okay, because we don't know how much time it's going to take. All right, before we didn't have a way to solve these out, but now since we are doing, log equations, and the previous lesson is all about solving log equations, we can actually do this. Okay, now the first step here, before you can switch this into log form right here, you need to get rid of the 150 out in front of E. So that's 150 times E raised to all that stuff. So since it's times, we're going to do the opposite. We're going to divide both sides. That'll be 2, and then equals E, and then raised to 0.055t. All right, and then from here, there's two approaches to solving these types of equations. I've always said just switch it to log form. So this is the way I kind of did it primarily on the previous lesson. So if you do that right here, start with your base. So it'll be log base E, which is actually natural log, of 2 equals that decimal. I'm going to go natural log. You can write it in the base if you want. Natural log of E, or I'm sorry, natural log of 2, and then equals this 0.055t. Okay, and then from there, then you can go and, I guess, divide natural log of 2 by 0.005 on both sides. I'll make that look prettier here in a second. So natural log of 2 divided by 0.055. I wrote that down wrong right here, but excuse me there. Okay. And that apparently is going to give us about 12.6 years once we type that into our calculator. So natural log of 2, whatever that decimal is, divided by 0.055 there. Now, another approach to solving that same equation, some people or some other teachers, I guess, will teach it this way here, which it really doesn't change that much. But they'll say, oh, take the log of both sides, or in this case, since it's E, take the natural log of both sides. So they'll put an ln over here on the left side, and then they'll go natural log of this stuff right here. So the natural log of 2, and then since you have natural log of E with base E right here, the E's are going to cancel out, and then you're going to be left with 0.055. Oh, I guess I forgot my T there. And then divide. So it kind of comes out to the same exact thing here, but I'd teach it more in the form of switch it to exponential form. So anyways, you'll get to the same exact thing. Apparently it'll be 12.6 years. Okay, so that is that. All right, and to get to 12.6 years, that's all in the calculator. I'm just kind of copying that from my notes here. So, all right, let's look at this next one here. Let's see if I can Make that a little bit smaller. Okay, Mr. and Mrs. Grosser invested $500 at 6.5 compounded continuously. What is the value of the investment after 7 years? Okay, so this will be another one of these. A equals compounded continuously, so this will be A equals P E raised to R times T. And we have the principal. They invested 500. They gave us the rate, 0.065, since you moved the decimal over twice. And then actually they gave us the time in this case here, so 7 right there. And then we need to solve for A, which A is really already by itself. So really you just type that into your calculator as one line right there. And then apparently we're going to get $788.09. So some of them you won't have to use a log. Usually we use a log to get to solve for like a certain exponent. So if we were solving for a rate, or if we were solving for time in this case, then we'd probably have to do something with the logs here. But since we have the entire right side right here, we just type that into the calculator and we'll get our answer. So you just got to be on the lookout for what type of problem they give you. Okay. Next one here on the next page. How long will it take for an investment of 500 to triple at 8% interest, compounded quarterly? How much will this investment be worth after 30 months? So yeah, in this case here, this is kind of a two-part question here. So first of all, it's asking how long will it take for it to triple. So that's asking for a time. And then actually, two, it's going to ask how much is investment worth after 30 months. So we got two parts of this here, but both parts are going to use A and then P and then compounded quarterly. So this will be R over N and then raised to N times T. Okay. So it said we started with $500 and we're trying to figure out when that's going to triple. So we'll put 1,500 out here. And then you got 1 plus your rate. Your rate, what was that? 8%, so 0.08. And then compounded quarterly, so we'll put 4 right there. And then we're going to raise that to N times T, so 4 times T. Okay. Now, there's a couple of approaches we can do here. We can actually go ahead and simplify everything inside of the parentheses. So I'm going to do that. So apparently when we do that, and you can just type it all in your calculator, that's going to be 1.02 right there, and then raised to 4t. Okay, now this is a common mistake right here at this next thing. A lot of people want to take these two and multiply them, all right? But the order of operation says to do whatever we have to the exponent first. So we technically need to do 1.02 raised to 4 times t, which we don't know t yet. But a way we can get around this 500 here out in front is actually divide both sides by 500. And that's, once again, that's a common mistake people make. So we're going to write this as 3 and then equals 102 and then raised to 4t. Okay, now as far as solving this goes, you can log both sides, but the way I usually teach it is take your base, switch forms, and then rewrite it here. So this will be log, and then the base is kind of weird. This is log base 1.02, and then of 3, and then equals 4t. Okay, and then from there we can figure out whatever that decimal is. In this case, I'm trying to see if I have it here in my notes. I don't. So we'll get whatever that decimal is here. Let me go ahead and grab a calculator. Bear with me real quick. Okay, so apparently that decimal gets us right here, 55. And then I'll go out a couple decimal places, 4781. And that's equal to 4 times t right there. Okay, and then from there, then we can go and divide both sides by 4. Okay, and then once we divide both sides by 4, apparently we're going to get about 13.9 once we round up, 13.9 years, I guess. Which basically you can almost just go ahead and round that up to 14. Depends on the instructions here. Let's see. They did not leave us any instructions on the rounding, so just whatever you want to do there on that. So 13.9 or about 14 years right there. And that's how to do that. And, you know, if you need help, just type in the logs for this decimal right here. You can actually use the log base button in your calculator. It's under math. Or you can use your change of base formula, which says log base 102 of 3 is the same thing as log of 3 divided by the log of 1.02. So anyways, if you need a recap on that, that would be 2 lessons ago. So anyways, second part is asking us how much is the investment worth after 30 months. So we actually don't know the final amount. So we'll go here and do 500 and then at 8%, so 0.08, and then divided by, I guess, N, which was compounded quarterly. And then here's the thing that's kind of weird about this here. You'll go 4 times T, but notice that they gave us the months instead of the years. So actually, to figure out how many years that is, we're going to do 30 divided by 12. Right, so 30 months divided by 12 years, or 12 months in a year, right there. And that comes out to, what did I do here? So that'll come out to about 2.5. So 2.5 years. So we'll go and plug that in here, 2.5. Okay, and then guys, actually you can type this all into your calculator as one line here, since we have everything on that right-hand side. And if you do that, apparently we're going to get $609.50. That's just kind of from my notes right there. So hopefully my notes are right. All right. So that's it on that. All right, next one here. This one's a little tricky here. You got a certain strain of bacteria can double every 40 minutes. So what is the approximate value up to 4 decimal places of K? How many organisms are there after 1 hour? How long will it take for the bacteria to reach 50,000 here? So I guess this is going to be kind of like a 3-part problem right here. So I guess write small. So I guess the big idea here at the beginning is we need to figure out the rate at which this thing is either growing or decaying. I'm assuming it's growing here because it's doubling every 40 minutes. Okay, so we're going to go back and use this continuous growing equation right here. So let's see here. It was y equals n and then e and then raised to k times t. So we're trying to find k, I guess is the growth constant is usually what they call it right here. So we're trying to figure out what k is. So here's how we do this here. So it doubles every 40 minutes. And they didn't give us any starting amount. But it doesn't really matter what the starting amount is. We just know it grows every 40 minutes. So for example here, if I had 1 of these bacterias, then my second value, my final value, better be 2. Or if I started out with, like, for example, 100, then I better have 200 at the end. So it really doesn't matter what numbers you use. So typically I'll start with 1, and then we'll end up with 2. So I'm going to go 1 raised to e, and then times or raised to the k value, which we don't know yet. And then t, we know was 40 minutes. So we'll plug in the 40 minutes right there. So our growth rate is going to be in terms of minutes, in this case here. Now, typically, no matter what numbers you used, whether you use 1 and 2 or 200 and 100, you would technically need to divide by whatever number is in front of e, which in this case, dividing by 1 doesn't really change anything. Okay. Now, the second step here after this, to go find the k value, we're going to have to switch forms. We have an unknown in the exponent. We have to use logs for this right here. So we're going to go and do log base e of 2 equals that entire exponent. Log base e, which is a natural log basically, So natural log base e of 2, and then equals 40 times k. Okay, and then after that, we can just do natural log of 2. That gives us some crazy decimal here. This decimal is 0.6931. Let's round it to 5 right here. And then that is equal to 40k. And then afterwards, I guess we will divide by 40. And then apparently our k value is going to be 0.0173 right there. It said 4 decimal values right there. Alright, and that is how you find your k value. Now I guess now that we have a k value, we can actually use our k value to answer these follow-up questions. And that's typically how they'll do these types of questions. They'll ask you to solve for a k and then use that k value. So hopefully you get the first part right, because you ain't going to get the second part right if you don't. So it's asking how many organisms are there after 1 hour right there. I guess they didn't give us a starting amount. So unless I'm reading this wrong. Alright, so let's assume they start with 1, I guess. So we'll say we'll use 1 for this example here. So they might have 200. I'm not sure. So they kind of left that part out there. So anyways, let's go with 1, and then we'll see how many there are after 1 hour. By the way, 1 hour, our rate is in minutes, so we need to go convert that 1 hour to 60 minutes. So be kind of careful there on that. Okay. I'm just trying to see if I forgot anything here. No? Okay. So, yeah, and apparently is 1. So we'll go 1 and then E, and then we're going to use that K value that we just got here. So it's 0.0173. And then 1 hour was 60 minutes. And then that'll be what we get right there. So you can just type that in, one line in your calculator. Apparently that will get to about 2.824 right here. And that would be, so you'd go from 1 to about 2.8 of those bacteria. Usually you would start with more than 1. Sometimes, maybe 100 is a good, better number to start with. But yeah, they left out that detail, I guess, here in the notes. So, yeah. So anyways, how long will it take for the bacteria to reach 50,000? So once again, they kind of left out a crucial piece of information here. So I guess we can use, I guess we'll use, I don't know, let's come up with an amount. Let's say for this part here, I'm just making this up here, they left this piece of information out. Let's just say n is 100. So let's see how long it takes for it to go from 100 to, I guess, about 50,000. So let's do this here. Let's go y equals, or actually, no, if we're going for how long it grows right here, we know the final amount. So we're going to put 50,000 right there. So I'll put 50,000 there. I'll put 100 here, since we're assuming we start with 100. And then we'll go e raised to the k value, which was 0.0173. And then we will, put a t right here. We don't know what t is. Okay, now like before, we want to get rid of that 100 out in front, so we're going to divide both sides by 100. Essentially, that's going to cancel out 2 zeros. So it's going to go to 500 and then e, and then raise to 0.0173 and then t. All right, and then since you got a variable in the exponent, you can't do anything with it. Start with your base, switch your form. So that's a natural log since it's base e. You can write e if you want, you don't need to. Natural log of 500 equals that decimal, 0.0173 times t. Okay, and then I guess we will take that log 500, whatever that is, or natural log 500. That apparently comes out to this decimal, 6.214. Let's go 6 right there. And then that is equal to 0.0173 t. Then I will divide both sides by 0.0173. And that'll come out to 359.2, minutes. in this case right here. And that's it. So once again, they left out a crucial information. They left out how many we started with here. So they should have put that, we can say, starting with whatever n value you want there. I guess I kind of changed it up there and wasn't consistent. Maybe I should have used 100 right here, but that's okay. So anyways, let's try the next few here. Got a few more just kind of like these here. And I don't think I have all these here in my notes, so we're going to have to wing it here. So this one here, the radioactive radium-226 decomposes with a half-life of 1800 years. Find the constant K for this isotope. Okay, so sometimes I'll use these weird numbers here, and I forget exactly what they tie to, but it has something to do with the category of the, whatever the material is. So anyways, it's an irrelevant number. The 226 doesn't mean anything on the problem here. But we know the half-life is 1800 years. So the way we start out with these half-life problems is we assume, okay, if we start with 2, we're going to end up with a 1 after 18,000 years. So that's actually what we're going to do in this case. Most of the times they don't give you the n in this case, so I just have to make up an n. Usually I do an even number, so I know what I'm starting with here. So let's say n is 2. Let's say the y value is 1. And then we're going to plug into y equals, and then n e raised to k t. Okay, and then we're going to plug in 2 out here in front. And then we're going to put in 1 right there for y. And then the k, we don't know what it is. And then we know the time is 1800 years. Okay, now you need to get rid of the 2 out in front. So we're going to divide both sides by 2. That'll just be 1/2 or 0.5. And then you have all this right here. We can't do anything as far as solving any further, so we switch forms. E raised to 1/2, or I'm sorry, not e, log base e, which we'll just call natural log. Natural log of base e of 1/2 equals, I guess, 1800k. All right, natural log of 1/2 is going to be, it's a negative number here. It's a negative 0.693. Let's go one more decimal. 1. Yeah, usually your k values go for at least 4 decimals. And then that's equal to 1800 k. So then I'm going to divide that by 1800. If I can type it in right. And then we get a k value. It's very, very small. My calculator here says negative 3.85. And then I guess 1. And then times 10 to the negative 4. If your calculator says all of this stuff, it says, all that stuff, e negative 4. That's the same exact thing as saying, in scientific notation, times 10 to the negative 4. Okay, which basically means your decimal's 4 hops over from where it should be. Or if you can count correctly here. So basically this is coming out to 0.0003, let's go A5. Kind of like that right there, and that's K. The reason I'm going so many decimal places there is just to make sure I get something kind of accurate. Okay, so then find the constant right there. That is it right there, and I guess that's all they're asking us to do there. Sometimes they'll ask you to go and use the constant, kind of like this last problem, to go solve for a second part. There you go. That's how you do all that. All right, let's see here. We got the Havital family wants to give their youngest daughter $20,000 when she is ready for college. So they have $11,500 to invest. How long will it take them to reach their goal? If their investment is compounded continuously at 8.3%, that's actually a pretty good rate right there, especially if they're already starting out with the $11,500. So anyways, compounded continuously, we're going to use A equals P E raised to R times T. And they're finding the time, and they're giving us everything else. We're starting with 11,500, and then trying to figure out how long it's going to get to 20,000. And then raise to E, and 8.3%, so 0.083 and then raised to, I guess, t. So we're trying to find that time value. Once again, to get rid of the 11,500, we're going to divide both sides. And, whoops, gonna mess that up here. Bear with me on this. My notes don't actually have everything worked out here. So this is 1.739. And then that's equal to, I guess, e, and then raised to 0.083 times time. And then let's switch forms again. We got log base c, so we'll go log base c is natural log of 1.739 is equal to this decimal 0.083t. Then take that decimal, whatever natural log of 1.739, that gets us about 0.553, and then we'll divide that by 0.083. And then that's t equals 6.67 years. And that is it right there. Okay, with this last one here, we're going to talk about the Newton's law of cooling. Now, first of all, I've seen the formulas written the way they are here, but I would go and change these little s's here to r's, just because it would make more sense to use those here, and here's why. With this formula that we're given here, T sub of R right here, T sub R, this is going to be the room temperature. And then T sub 0, this is also called T naught. This is going to be the initial temperature. And then they also had T sub, or not even T sub, T of T right here. So this will represent the final temperature, I guess. Or the current. You can even say like the current temperature right there. So this one's a little bit of a long one here, but this is how you can use logs and stuff to go and figure out the time of someone's death here. So a lot of, I guess, police and FBI, they'll use this a lot here to go and do this. So the police discover the body of a Flower Mound math teacher. Oh no. Critical to solving the crime is determining when the murder was committed. The coroner, I guess, arrives at the murder at 12:30. She immediately takes the body temperature and finds it to be 93.6 degrees at 12:30. She immediately takes the body temperature and then finds it to be, I already read that. She takes the temperature again 1 hour later and finds it to be 92.4 degrees Fahrenheit. The temperature of the room is 70 degrees Fahrenheit. At what time was the murder committed? Normal body temperature is 98.6 degrees Fahrenheit. So what we're going to do here, since she takes the temperature after 1 hour after she gets there and she does the initial temperature, is we're going to figure out using those two values there what the K, or what the decay rate of the temperature is for that room temperature and the starting temperature. So we're going to plug everything we know into this formula. So it's kind of weird at first here, but the way I would start this out here is the initial amount, or the initial temperature when she gets there, which is going to be T sub 0 right there. That was, I believe, 93.6. All right, and apparently the formula says we're going to subtract the room temperature, T sub R, which was 70 degrees. And we're also going to put that out here in front. That's what the formula calls for. And then you got E raised to K. We don't know what K is, but we know the time that we spent was 1 hour right there. And then we know the final temperature after that 1 hour. That's what the left side's going to equal. This was the 92.4. Okay. So now we got a log equation or an exponential equation that we're going to use a log to eventually solve for. So what I would do first here is I would get rid of this 70 since it's not really attached to anything. We're going to subtract 70. We get, I guess, what is that, 22.4. Okay, I guess we can simplify inside of the parentheses. So that would be 23.6. And we got e raised to k times 1, or just e raised to k. Now before you can switch to log form, or actually natural log form, we need to get rid of this thing in front of the base, or in front of e. So we're going to divide both sides by 23.6. And let me use my calculator here for that. 22.4 divided by 23.6 comes out to 0.949. Let's go to 2, I guess. Okay. Now after this, we're going to switch this to log form. So you have log base e, which is a natural log. So we'll go natural log of 0.9492. And apparently that is equal to the k. We don't have to worry about dividing anything here. So I'm just going to hit natural log of that decimal. And that comes out to negative 0.0521 right there. And that's our k value. It's negative because the temperature is going down. Okay, now that doesn't tell us what our answer is. That just tells us at the rate at which the temperature is decreasing given the temperature in the room. So this starts the second part of the problem here. Now we're trying to figure out how much time has passed. We're going to figure out a new time value here. So it's real important that we know what time she started at is at 12:30, and we know that initial temperature, or actually we don't know that initial temperature. We know the temperature that she measures there, but we know the initial temperature that the person was at 98.6. So what I'm going to do is now I'm going to treat that as the initial temperature of the person. So I'm going to go inside of the parentheses. We'll do the 98.6, and then we'll subtract the room temperature. And I think we have the room temperature out here in front again. And then when they get there at the, I guess at the 12:23, they know that her initial temperature when they found the body was at 93.6. So I'm going to put that right there. And then we don't know how much time has passed, so we're going to leave t as t, but then we need to use that decimal that we just got from this k value. So I'm going to go plug that in up here. That was negative 0.0521. So now you got this log equation right here, and essentially we need to go figure out t. All right, and by the way, since I think we said it was 1 hour, our t will be in hours as well. So it's kind of the same idea. We'll subtract 70 to start out with. So that'll get us 23.6 again. Here inside of the parentheses, we'll get, I guess, 28.6. And then, oh, I forgot my e. I was like, that looks weird. E, and then raise to negative 0.0521 t. Okay, like before, we need to get rid of that 28.6 out in front of e, so we're going to divide to do that. So let me punch that out here real quick. 28.6. So that'll be 0.8252, I guess. And then that's going to equal e raised to this weird decimal. Okay, and then after that, we're going to switch forms. We're going to go log of e, or log base e, of that decimal, equals all this stuff here. So log of 0.8, not even log, it's natural log. Natural log of 0.8252, then equals this negative 0.0521 t. So whatever the natural log of 0.8252 right there, that's going to get us negative 0.1921. And I guess we're going to divide here after this. We'll divide by the negative 0.0521. And then that gives us T is 3.68 right here. And actually, I guess we can round that to 69 right there. Okay, and that is how many hours has passed right there. So that's probably like, a little bit harder and a little bit more work than what you're gonna, be expected to do. Especially they didn't do a good job in this problem defining the variables. But once we define it, we just use that formula there. And once again, that's the number of hours. So if we want to take the number of hours and then apply that to the 1230, some people might say, oh, okay, it's about, 4 hours ago. You could, I guess, do that if you wanted. If you want to get real fancy with this here, we can say it was 3 hours. And then if you want to take that 0.69 hours right there and convert that into minutes so we can get a little bit more of a precise time, we can take 0.69 hours. We can divide by 60. Or I'm sorry, no, that would be times 60 right here. Times it by 60 to get the number of minutes. So if I go 0.69 times 60, that'll give me about 41 minutes. Yeah, 41.4, or you can say 41 minutes. So it happened 3 hours and 41 minutes ago. And then I think when you subtract that from the 12:30 time, I guess that would be at about 9, but then subtract 41 minutes would be like at 8. I think 8:49 right there, and then we could say a.m. And that would be your time of death right there, apparently. So, that's something that would be kind of useful because then they could go, track down, or maybe look at, security cameras at that time and see if they can find anything or ask around people. But there you go. There's a real world application right there of using some log equations. So anyways, that is it here for today.